Right now, as you're watching this video, something extraordinary is happening in our solar system. An object from beyond our cosmic neighborhood, C2024 S1, better known as Atlas, is racing toward the Sun at over 100,000 miles per hour. And on October 29th, something remarkable is going to happen. On that date, Atlas will reach perihelion, its closest approach to the Sun, at precisely the moment when Earth is on the opposite side of our star. For weeks, this interstellar visitor will be completely hidden from every telescope on our planet, concealed behind the Sun's overwhelming glare. Now, here's where this gets absolutely mind-blowing. Harvard astrophysicist Dr. Avi Loeb has suggested that this timing might not be coincidental, that October 29th represents what he calls the opportunity, the perfect moment for Atlas to use the Sun's gravity to brake, to slow down, to potentially trap itself in our solar system forever. But before you dismiss this as science fiction, let me show you the data. Because in the last 48 hours, new calculations have emerged that make this story even more extraordinary. We're talking about an object with a minimum mass of 33 billion tons, far more massive than anyone initially predicted. We're talking about chemical compositions that break every rule we know about comets. We're talking about a green glow that appeared at precisely the moment it shouldn't have been possible. Today, we're going to do a deep dive into one of the most controversial astronomical observations of the decade. We'll examine Dr. Loeb's claims with scientific rigor, explore what the actual data shows us, and understand why October 29th might represent one of the most significant dates in modern astronomy. Whether Atlas turns out to be a remarkable natural phenomenon or something far more intentional. By the end of this video, you'll understand the real science behind interstellar objects, the legitimate mysteries that keep astronomers up at night, and exactly what we should be watching for when Atlas disappears behind the Sun in just a few weeks. If you're ready to explore the boundaries of what we know about our cosmic visitors, hit that like button and subscribe. And drop a comment telling me where you're watching from, because this is a story that's unfolding in real time, and your observations might be more important than you realize. Let's get into it. What makes an object interstellar? Before we dive into the Atlas controversy, we need to understand what makes an object interstellar and why these cosmic wanderers are so scientifically valuable. Our solar system contains trillions of objects: planets, moons, asteroids, comets, and countless chunks of rock and ice. Every single one of these objects is gravitationally bound to our Sun. They orbit in predictable paths, following trajectories determined billions of years ago when our solar system formed. But interstellar objects are different. These are cosmic nomads, objects that were born around other stars, ejected from their home systems through gravitational interactions, and now drift through the galaxy. When we detect them passing through our solar system, they're not orbiting our Sun. They're just passing through, like travelers crossing through a town on their way to somewhere else. The key signature of an interstellar object is its hyperbolic trajectory. When astronomers calculate an object's orbit, they determine something called orbital eccentricity. Objects bound to the Sun have eccentricities less than 1. They're on closed, elliptical orbits. But interstellar objects have eccentricities greater than 1, meaning they're on open, hyperbolic paths. They're moving so fast that the sun's gravity can't capture them permanently. Atlas has an orbital eccentricity significantly greater than 1, confirming beyond doubt that it originated from interstellar space and, under normal circumstances, would return to interstellar space after its brief visit. The historic context: our 3 interstellar visitors. Atlas isn't the first interstellar visitor we've detected. In fact, it's the 3rd confirmed interstellar object to pass through our solar system, and understanding the first 2 is crucial for appreciating why Atlas is generating so much scientific debate. 1ie Oumuamua, 2017. This cigar-shaped object was the first confirmed interstellar visitor ever detected, and it absolutely revolutionized astronomy. What made Oumuamua so controversial was its anomalous acceleration, a slight but measurable change in velocity that couldn't be fully explained by the sun's gravity alone. This unexplained acceleration sparked intense debate. Was it outgassing like a comet? But we never detected any gas or dust tail. Was it being pushed by solar radiation pressure? That would require it to be extraordinarily flat and thin, basically a cosmic pancake. Or, and this is where Dr. Loeb first entered the conversation, could it be artificial? An alien light sail? The truth is, we still don't know what Oumuamua was. We detected it too late, after it had already passed its closest approach to the sun. And by the time we realized its significance, it was leaving the solar system. We never got close-up observations. The mystery remains unsolved. 2i Borisov, 2019. This visitor was completely different. It looked and behaved exactly like a comet. It had a coma, a glowing cloud of gas. It had a tail, and it was actively releasing gas and dust as it approached the sun. In many ways, Borisov was comforting to astronomers because it matched all expectations for what an interstellar comet should be. But even Borisov had surprises. Its composition was subtly different from solar system comets. It had unusually high levels of carbon monoxide and a different gas-to-dust ratio. These chemical differences tell us that the planetary system it came from had different formation conditions than our own. See 2024 S1 Atlas, 2025. And now we have our 3rd visitor. Discovered on July 1st, 2025 by the Atlas Survey in Chile, this object is generating controversy that exceeds even the Oumuamua debate. And to understand why, we need to look at what makes Atlas so unusual. The Atlas Survey, our cosmic sentinel. The discovery of Atlas wasn't luck. It was the result of a sophisticated early warning system. The Asteroid Terrestrial Impact Last Alert System, ATLAS, consists of 4 robotic telescopes stationed around the world, automatically scanning the entire visible sky every night. Atlas was built primarily to detect potentially hazardous asteroids, space rocks that could collide with Earth. But it's also become our best tool for discovering interstellar visitors because it looks at huge swaths of sky repeatedly, comparing images to detect anything that moves against the background stars. The fact that Atlas has discovered this 3rd interstellar object tells us something important. We're getting dramatically better at detecting these cosmic wanderers. Before 2017, we had never confirmed a single interstellar object. Now we've found 3 in 8 years. This improvement isn't because more objects are suddenly entering our solar system, it's because our detection capabilities have massively improved. Which raises a mind-blowing question. How many interstellar visitors passed through our solar system before we had the technology to detect them? How many are passing through right now, too small or too dark for even our best systems to spot? Now let's examine Dr. Avi Loeb's arguments systematically. I want to be clear. Dr. Loeb is a tenured professor of astronomy at Harvard University, former chair of Harvard's astronomy department, and a respected theoretical physicist. When he makes claims, they deserve serious consideration, even if they're controversial. But we also need to separate what the data actually shows from interpretations of that data. So let's go through each anomaly one by one. Anomaly number 1, the size and mass problem. When Atlas was first discovered, initial brightness calculations suggested it might be approximately 20 kilometers in diameter. That's bigger than Manhattan Island, roughly twice the size of the asteroid that ended the dinosaurs 66 million years ago. Dr. Loeb immediately recognized this as statistically problematic. Here's why. Space debris, whether asteroids, comets, or interstellar rocks, follows what's called a power law distribution. This means for every large object, there are exponentially more smaller objects. If there's one rock that's 10 kilometers across, there might be 100 rocks that are 1 kilometer across, 10,000 rocks that are 100 meters across, and 1,000,000 rocks that are 10 meters across. Based on our understanding of how much rocky material exists in interstellar space, Loeb calculated that we should find an object the size of the initial Atlas estimate only once every 10,000 years. Yet we've been systematically searching for interstellar objects for barely a decade, and we found one. Those are extraordinary odds. More recent observations have refined the size estimate. Hubble Space Telescope data from late August 2024 suggested an upper limit of about 5.6 kilometers in diameter, still large, but not the initially estimated 20 kilometers. However, here's where things get really interesting. In September 2024, Dr. Loeb and colleagues published new trajectory analysis based on 4,000-plus observations from 227 observatories worldwide. What they found was surprising. Atlas shows almost no non-gravitational acceleration. Let me explain why this matters. When a comet approaches the Sun and heats up, ice on its surface sublimates, turns directly from solid to gas. This outgassing acts like tiny rocket engines, pushing the comet slightly and changing its trajectory in measurable ways. We call this non-gravitational acceleration, and it's one of the defining characteristics of active comets. But Atlas isn't showing this behavior, at least not to the degree we'd expect. Its trajectory matches a purely gravitational path to within incredibly tight margins. Yet we know Atlas is outgassing. The James Webb Space Telescope observed it on August 6th and measured gas coming off its surface at a rate of about 150 kilograms per second. That's enough material to produce measurable thrust on a typical comet. So, why isn't Atlas being pushed around by its own jets? Dr. Loeb's answer? It's too massive. Given the observed outgassing rate and the absence of detectable non-gravitational acceleration, Loeb calculated that Atlas must weigh at least 33 billion tons. That's the minimum mass required for the outgassing to not noticeably affect its trajectory. Think of it this way: trying to push a cruise ship with a leaf blower. The force is there, but if the mass is large enough, the acceleration is negligible. Now here's the puzzle. If Atlas weighs 33 billion tons, but has a diameter of only 5 to 6 kilometers, we can calculate its density. And depending on its exact size, it might be less dense than we'd expect for a solid rock and ice comet. This raises an intriguing possibility that Dr. Loeb hints at. What if Atlas isn't solid? What if it's hollow? A shell with a lot of volume but not much mass per unit volume. A hollow structure could explain the observations. Massive enough to resist outgassing thrust, but light enough per unit volume that it's not as implausibly rare as a solid 20-kilometer object would be. Important. This is speculation, not confirmed fact. We have no direct evidence that Atlas is hollow, but the mass-to-size ratio does present an interesting puzzle that deserves further investigation. Anomaly number 2, the trajectory alignment. Here's where the statistical arguments start to stack up in ways that make even skeptical astronomers pause. Our solar system is relatively flat. The 8 planets orbit the Sun in roughly the same plane. This is called the ecliptic plane. This flatness is a remnant of how our solar system formed from a rotating disk of gas and dust billions of years ago. But interstellar objects shouldn't care about our ecliptic plane. They come from other star systems with their own orientations. When something arrives from interstellar space, it should come from a random direction at a random angle. Atlas arrives on a path that's aligned with the ecliptic plane to within about 5 degrees. Dr. Loeb calculates the random probability of this happening at approximately 1 in 500. Not impossible, but certainly notable enough to raise an eyebrow. But it gets more interesting. Atlas's trajectory brings it close to multiple planets. October 3rd, 2024. Close approach to Mars, 29 million km. Close approaches to Venus and Jupiter at favorable orbital positions. Dr. Loeb calculated the combined probability that an interstellar object on a random trajectory would pass this close to Jupiter, Mars, and Venus at times when they're in the right positions in their orbits. His answer: approximately 1 in 20,000. Now, we need to be careful here. These probability calculations depend on assumptions about what counts as close and how you define the parameters. Critics argue that with enough cherry-picking of parameters, you can make almost anything look statistically unlikely. But Dr. Loeb's point is valid. When multiple low-probability events stack up, it's worth asking whether they're truly independent coincidences or whether there's an underlying pattern. Now let's examine the other side of this debate, because good science requires considering all viewpoints. NASA's position. It's a comet. NASA's Dr. Tom Statler, program scientist for small bodies, has stated repeatedly that all available data points to Atlas being a natural comet. The evidence supporting this conclusion: it has a coma and tail, confirmed by multiple observations since August. It shows outgassing behavior consistent with sublimating ices. Its brightness variations match what we expect from a rotating, irregularly shaped icy body. Its chemical composition, while unusual, falls within the range of natural variation observed in other comets. Dr. Statler and other NASA scientists argue that comets are inherently unpredictable and messy objects. Even comets from our own solar system behave in ways that can seem anomalous until you understand the physics. They brighten and dim irregularly. They develop unexpected jets. They sometimes fragment. Unusual behavior doesn't automatically imply artificial origin. The motion artifact explanation. The forward glow that appeared in early Hubble images has been thoroughly explained as a tracking artifact. When telescopes track a fast-moving object against the background of stars, the stars streak in one direction while the object appears stationary, or vice versa, depending on how the tracking is set. This can create misleading visual effects that look like extended structures or unusual orientations. By August, when better images were obtained, Atlas showed a completely normal comet tail streaming away from the sun. The observational bias problem. Critics point out that many of Dr. Loeb's probability calculations may suffer from selection bias and observer effects. For example, ecliptic alignment. We're more likely to detect objects that pass through the inner solar system near the ecliptic plane, because that's where most of our telescopes are pointed, and where most asteroids and comets reside. Objects coming in at steep angles might pass through undetected. Planetary encounters. We notice and publicize interstellar objects that pass near planets because those encounters are scientifically interesting. Objects that don't pass near anything notable might go unremarked. October 29th. Timing. With 365 possible days in a year, having any specific date occur has a 1/365 probability. The fact that perihelion happens to coincide with solar conjunction might simply be a coincidence we're noticing after the fact. The criticism is essentially this: when you look at enough data points, some will appear statistically unlikely just by chance. This is called the multiple comparisons problem in statistics. If you test enough hypotheses, some will appear significant even if there's no underlying pattern. The extraordinary claims problem. Dr. Chris Lintott from Oxford University has been particularly blunt, calling the alien technology hypothesis absolute nonsense. His argument, extraordinary claims require extraordinary evidence. Proposing that Atlas is alien technology is an extraordinary claim. It would confirm that we're not alone in the universe, that another civilization has mastered interstellar travel, and that they're currently visiting our solar system. Given the magnitude of this claim, we should require correspondingly strong evidence. And according to critics, the evidence for Atlas being technological simply isn't there. Every anomaly has plausible natural explanations. The mass can be explained by a dense, solid comet nucleus. The trajectory alignment could be observational bias. The October 29th timing could be coincidence. The early activity could be volatile-rich composition. The chemical composition is unusual, but not impossible naturally. When natural explanations exist, Occam's razor suggests we should favor them over invoking alien technology. The Oumuamua precedent. Critics also point to the Oumuamua controversy as a cautionary tale. Loeb was one of the primary proponents of the idea that Oumuamua might be an alien light sail, based on its unexplained acceleration. That claim was widely criticized by other astronomers, who showed that natural mechanisms, including outgassing of hydrogen ice or radiation pressure on a tumbling, highly elongated object, could potentially explain the acceleration without requiring alien technology. The pattern, critics say, is that Dr. Loeb tends to favor exotic explanations for phenomena that have more mundane solutions. This doesn't mean he's wrong, but it does suggest we should be cautious about accepting his interpretation without strong supporting evidence. So we've examined the arguments and counter-arguments. Now let's talk about what we can actually observe and what we should be watching for. The perihelion pass. On October 29, 2024, Atlas will reach its closest approach to the Sun at approximately 1.44 astronomical units, just inside the orbit of Mars. At this moment, Earth will be on the opposite side of the Sun. Atlas will be in solar conjunction. Direct observation from Earth will be nearly impossible for several weeks. If Atlas were to make a braking maneuver using the Oberth effect, this would be the optimal time. A relatively small change in velocity at perihelion could transition the object from a hyperbolic escape trajectory to an elliptical bound orbit. How would we detect this? We wouldn't, at least not immediately. We'd only know weeks later, when Atlas re-emerges from behind the Sun in late November or early December, and we recalculate its orbital elements. If the orbit has changed, if Atlas is no longer on an escape trajectory, that would tell us something extraordinary happened. It would require some form of propulsion, because natural gravitational interactions with the Sun alone can't capture an object that's already on a hyperbolic trajectory. What we'll actually be watching? Several spacecraft and observatories will have opportunities to observe Atlas during and after the perihelion pass. October 3rd, Mars Reconnaissance Orbiter. NASA's HiRISE camera will attempt to image Atlas during its close approach to Mars. HiRISE has extraordinary resolution and should be able to separate the nucleus from the surrounding coma, giving us the best size estimate yet. November, ESA's JUICE spacecraft, the Jupiter Icy Moons Explorer, currently en route to Jupiter, will have good viewing angles of Atlas as it emerges from solar conjunction. Late November, early December, ground-based telescopes. When Atlas reaches its closest approach to Earth, still about 170 million miles away, our best telescopes, Hubble, Webb, and ground-based observatories will have excellent viewing opportunities. March 2026, Juno at Jupiter. NASA's Juno spacecraft orbiting Jupiter will observe Atlas during its passage through the Jupiter system. The key questions. Here's what scientists will be looking for. Does the orbit change? If Atlas emerges from perihelion on a different trajectory than it went in on, that would be extraordinary and would demand explanation. Does the size estimate change? HiRISE observations should resolve whether Atlas is closer to 5 kilometers or 15-20 kilometers in diameter, which dramatically affects the mass budget calculations. Are there any structural anomalies? High-resolution images might reveal unusual shapes, geometric patterns, or surface features inconsistent with natural formation. Does activity pattern change? If outgassing suddenly increases, decreases, or shows directed jets after perihelion, that could indicate something unusual. Are there any electromagnetic emissions? Radio? Telescopes will be listening for any signals that might indicate active technology. Whether Atlas turns out to be a natural comet or something more exotic, this case highlights several important truths about modern astronomy and the search for extraterrestrial intelligence. We're living in a golden age of discovery. The fact that we've detected 3 interstellar objects in 8 years is remarkable. Before 2017, we had detected 0 confirmed interstellar visitors in all of human history. This rapid discovery rate tells us that interstellar objects are common. Based on current detection rates, astronomers estimate there could be thousands or even tens of thousands of interstellar objects passing through our solar system at any given time. Most are too small or too dark for us to detect, but they're out there. The Vera Rubin Observatory, which recently came online, will revolutionize this field. It scans the entire visible sky every few nights with unprecedented sensitivity. Scientists predict it will detect interstellar objects regularly, perhaps several per year. Each detection is a free sample of material from another star system. Each one teaches us about planetary formation in different stellar environments, and each one offers the tantalizing possibility that we might encounter something that isn't entirely natural. The nature of scientific controversy. The Atlas debate illustrates something important about how science works, and sometimes doesn't work. Science is supposed to follow evidence, but scientists are human. We have biases, career concerns, and reputational risks. Proposing radical hypotheses can damage your credibility, even if you have legitimate reasons for proposing them. Dr. Loeb argues that the scientific community is too conservative, too quick to dismiss unconventional possibilities without thorough investigation. His critics argue that he's too eager to invoke exotic explanations for phenomena that have mundane solutions. Both perspectives have merit. Good science requires balancing open-mindedness with skepticism. We should investigate unusual observations carefully, but we should also favor simpler explanations when they fit the data. The tension between these approaches is healthy. It's how science makes progress, through vigorous debate, competing hypotheses, and ultimately, evidence that settles disputes. The search for techno-signatures. The Atlas case is also relevant to the broader search for extraterrestrial intelligence, SETI. Traditional SETI focuses on detecting radio signals from distant civilizations, but there's growing interest in searching for techno-signatures, physical evidence of technology rather than just electromagnetic signals. Interstellar objects represent a potential techno-signature category. If advanced civilizations exist and have been exploring the galaxy for millions of years, some of their probes might still be wandering between stars. We might encounter derelict spacecraft, inactive probes, or artifacts from civilizations long extinct. How would we recognize them? This is genuinely difficult. An advanced civilization's technology might look nothing like ours. They might use propulsion systems we can't detect, construct probes from materials we'd mistake for natural rock, or employ stealth technologies that make detection nearly impossible. Dr. Loeb's proposed solution is systematic observation and classification. His Loeb scale 0-10 rating for how likely an object is to be technological is an attempt to create a framework for evaluating interstellar visitors without either dismissing anomalies too quickly or seeing aliens everywhere. We need better protocols for this. As we detect more interstellar objects, we need standardized observation procedures, clear criteria for what constitutes anomalous behavior, international coordination for rapid response, protocols for attempted communication, if we detect something genuinely artificial. Right now, we have none of this. We're making it up as we go. The October 29th test case. Atlas, whether natural or not, serves as a test case for how humanity handles potential cosmic visitors. The scientific community's response to Dr. Loeb's claims reveals both strengths and weaknesses. Strengths: rapid analysis and counter-arguments from multiple independent researchers, public data sharing and peer review, willingness to engage with unconventional hypotheses. Weaknesses: defensive reactions and ad hominem attacks rather than purely data-driven responses. Lack of coordinated observational campaigns. No clear institutional framework for investigating high-priority targets. If Atlas were genuinely artificial, which to be clear is extremely unlikely based on current evidence, we're not prepared to respond effectively. We have no international body responsible for verifying techno-signatures, no protocols for attempted communication, no plans for what to do if something responds. October 29th gives us an opportunity to think through these scenarios. Even if Atlas turns out to be entirely natural, the next interstellar visitor might not be. And when that day comes, if it comes, we should be ready. So where does this leave us? What the evidence actually shows? Let's be clear about what we can say with confidence. Confirmed facts. Atlas is definitely an interstellar object on a hyperbolic trajectory. It has a minimum mass of approximately 33 billion tons based on trajectory analysis. It shows active outgassing and comet-like features. Its chemical composition is unusual but not unprecedented. Its trajectory brings it close to multiple planets. Perihelion occurs on October 29th when Earth is on the opposite side of the Sun. Reasonable scientific questions. Why is the mass so high given the size estimates? Why was it bright and active so far from the Sun? Are the trajectory alignments statistically significant, or selection bias? What explains the chemical composition anomalies? Speculative interpretations. Could Atlas be hollow rather than solid? Could the October 29th timing indicate intentional design? Could this be a technological object rather than a natural comet? Current scientific consensus. Most astronomers believe Atlas is a natural interstellar comet with some unusual but explicable properties. The anomalies, while interesting, do not rise to the level of requiring exotic explanations. Continued observation is warranted, but there's no compelling evidence for artificial origin. What happens next? Over the coming weeks and months, we'll get answers to many of these questions. October 3rd. High-rise. Images from Mars. Reconnaissance orbiter should give us the best size estimate yet. October 29th. Atlas reaches perihelion while hidden from Earth's view. Late November. Atlas re-emerges from behind the Sun. Orbital calculations will reveal whether anything changed during the perihelion pass. December, closest approach to Earth, providing optimal viewing conditions for detailed observations. March 2026, observations from Juno as Atlas passes Jupiter. Verdict: by early 2026, we should have enough data to conclusively determine whether Atlas is simply an unusual natural comet or something that requires more exotic explanations. The responsible way forward. Here's what I believe we should do. Observe systematically. Use every available telescope and spacecraft to gather comprehensive data. Analyze objectively. Follow the evidence wherever it leads without predetermined conclusions. Communicate clearly. Distinguish between confirmed observations, reasonable hypotheses, and speculative interpretations. Prepare for possibilities. Develop protocols for how we'd respond if we ever do encounter artificial interstellar technology. Stay curious. Keep asking questions, even uncomfortable ones, because that's how science advances. Dr. Loeb may or may not be correct about Atlas, but he's correct about this. We should be watching carefully, gathering good data, and keeping an open mind about what we might find. The universe has surprised us before, and it will surprise us again. My personal take. Having examined all the evidence, here's my honest assessment. Is Atlas alien technology? Almost certainly not. The evidence for artificial origin is suggestive, but far from compelling. Every anomaly has at least one plausible natural explanation, and Occam's razor suggests we should favor the simpler hypothesis. Is Atlas worthy of intense scientific scrutiny? Absolutely yes. Whether it's natural or artificial, it's an unusual object that can teach us about interstellar environments, planetary formation in other star systems, and the diversity of cosmic chemistry. Is Dr. Loeb's approach valuable? Yes, with caveats. His willingness to ask uncomfortable questions and challenge scientific orthodoxy is important. Science needs people willing to explore unconventional hypotheses. But we also need to be rigorous about distinguishing between interesting anomaly worth investigating and compelling evidence for extraordinary claims. Should we be preparing for the possibility of encountering artificial interstellar objects? Yes, even if the probability is low, the implications are so significant that having protocols and frameworks in place makes sense. We don't need to assume every weird rock is an alien probe, but we should know what to look for and how to respond if we ever do find one. Now let's explore some of the fascinating science behind interstellar objects that often gets lost in the controversy. How do objects become interstellar? Understanding how objects get ejected from their home star systems helps us appreciate what we're seeing when we detect interstellar visitors. Gravitational slingshots. When planets form, they don't settle into perfectly stable orbits immediately. Young planetary systems are chaotic, with planets migrating, colliding, and gravitationally scattering debris. When a small object passes close to a massive planet at just the right angle and velocity, the planet's gravity can accelerate it beyond the star system's escape velocity, sending it on a one-way trip into interstellar space. Multi-body interactions. Sometimes multiple planets conspire to eject objects. An asteroid or comet might receive gravitational kicks from several planets in succession, each interaction adding energy until the object achieves escape velocity. Stellar encounters. Young star systems often form in clusters where stars are relatively close together. When two stellar systems pass near each other, their gravitational interaction can disrupt planetary systems and fling objects into interstellar space. Supernova explosions. When massive stars explode, the blast wave can completely destroy any planetary system, scattering debris across light years of space at tremendous velocities. Computer simulations suggest that planetary systems typically eject far more mass than they retain. For every kilogram of material that ends up in stable planets and asteroids, several kilograms might be ejected into interstellar space. This means the galaxy is filled with wandering debris, the leftovers of planetary formation. Most of it is small: pebbles, boulders, house-sized rocks. Large objects like Atlas are rare, which is why their detection is statistically surprising. The journey through interstellar space. Once ejected, these objects begin journeys that can last millions or even billions of years. Cosmic rays. Space between stars isn't empty. It's filled with high-energy particles called cosmic rays, mostly protons traveling at nearly the speed of light. These constantly bombard interstellar objects, gradually altering their surface chemistry and creating new compounds through radiation processing. Interstellar dust. Objects also encounter dust grains drifting through space. At interstellar velocities, tens of kilometers per second, even tiny grains hit with tremendous energy, slowly eroding surfaces and potentially coating them with new material. Interstellar gas. Diffuse clouds of hydrogen, helium, and heavier elements pervade the galaxy. Objects passing through these clouds can accumulate surface deposits, essentially cosmic frost forming over millions of years. Temperature. Far from any star, space is cold, about 2.7 Kelvin, 270 degrees, just above absolute zero. Any volatiles on an interstellar object's surface gradually sublimate away over time, leaving only the most stable compounds. This is why interstellar objects are so scientifically valuable. They've experienced environmental conditions completely different from anything in our solar system. Their surfaces have been processed by cosmic rays for millions of years. Their compositions might reflect the chemistry of star-forming regions from different eras of galactic history. Why are they so fast? When we detect interstellar objects, they're always moving incredibly fast, typically 20 to 40 kilometers per second relative to our Sun. This isn't because they have propulsion, it's because of galactic orbital mechanics. Everything in the Milky Way orbits the galactic center. Our Sun moves at about 220 kilometers in its orbit. Other stars have different orbital velocities depending on their distance from the galactic center and their position in the galactic disk. When an object is ejected from another star system, it retains that system's orbital velocity around the galaxy. If that star was moving in a significantly different direction than our Sun, the relative velocity between us and the ejected object can be quite high. Additionally, the ejection process itself adds velocity. Gravitational slingshots from giant planets can accelerate objects to 10 to 20 kilometers per second. relative to their home star. Combined with the orbital velocity differences, this results in the high speeds we observe. The detection challenge. Finding interstellar objects is extraordinarily difficult. Here's why. They're small. Even a 20-kilometer object is tiny on astronomical scales. At the distances where we typically detect them, beyond Mars's orbit, they appear as faint points of light. They're dark. Many are composed of rock and ice that reflects only a small fraction of sunlight. They can be 10 to 100 times dimmer than asteroids of the same size in our solar system. They're fast, moving at 20-40 km/s. They cross the inner solar system in just a few months. If you're not looking at the right patch of sky at the right time, you miss them completely. They look like asteroids. Without precise trajectory measurements over several nights, interstellar objects are indistinguishable from the millions of asteroids orbiting the Sun. Only after careful orbital calculations do we realize they're on hyperbolic trajectories. This is why we only started detecting them recently. We needed wide-field survey telescopes that scan large areas of sky repeatedly, fast computers to process millions of observations and flag unusual objects, automated systems that can recognize potential interstellar visitors and trigger follow-up observations, international networks that can track objects 24/7 as Earth rotates, the Atlas system, Pan-STARRS, and now the Vera Rubin Observatory provide these capabilities. We're finally catching up to technology levels needed to detect what has always been passing through our cosmic neighborhood. What future missions could teach us? The Holy Grail would be sending a Omni spacecraft to intercept an interstellar object for close-up study. The challenge. Interstellar objects are moving too fast for conventional spacecraft to catch. Matching velocity with something traveling 30 km/s relative to the Sun would require enormous amounts of fuel, far more than any current spacecraft carries. Possible solutions: fast flyby missions. Instead of matching velocity, a spacecraft could perform a high-speed flyby, gathering data during a brief encounter lasting minutes or hours. This was proposed for Oumuamua, but never funded. Ready and waiting probes. Keep a spacecraft on standby in Earth orbit, fueled and ready to launch immediately when an interstellar object is detected. Use Jupiter gravity assists to boost velocity and intercept the target while it's still in the outer solar system. Project Lyra, a theoretical mission concept that would use multiple gravity assists and possibly a solar Oberth maneuver, diving close to the Sun to maximize propulsion efficiency, to catch up with departed interstellar visitors. Breakthrough Starshot. Technology. Ultra-lightweight spacecraft propelled by powerful lasers could potentially achieve the velocities needed to catch interstellar objects. This technology is being developed for interstellar missions, but could be adapted for closer targets. Imagine what we could learn from a close-up mission: detailed surface composition and mineralogy, interior structure from radar penetration, direct sampling of material for laboratory analysis, high-resolution imaging, revealing formation. History. Detection of any magnetic fields, charged particles, or other physical properties. Such a mission could definitively answer questions that telescopic observations can only hint at. Is the object solid or hollow? Is its composition natural or engineered? Are there any signs of artificial structure? The Atlas story, regardless of how it resolves, raises profound questions about humanity's place in the universe. Are we alone? The Fermi paradox asks, if intelligent life is common in the universe, where is everyone? The galaxy is billions of years old and contains hundreds of billions of stars. Even if intelligent life is rare, there should have been countless civilizations that arose before us. Some should have achieved interstellar travel. Some should have spread across the galaxy, leaving behind artifacts, probes, and evidence of their existence. So why haven't we found any? Possible answers: we are alone. Perhaps life is so rare, and intelligence even rarer, that we're the first in our region of the galaxy. This would make us extraordinarily special and extraordinarily lonely. They're out there but haven't reached us. Space is vast. Even civilizations that achieved interstellar travel might not have reached our particular corner of the galaxy yet. They're hiding. The Dark Forest. Hypothesis suggests civilizations stay silent to avoid attracting attention from potentially hostile species. They're unrecognizable. Advanced civilizations might have transcended physical form, uploaded consciousness to computers, or developed in ways so alien we wouldn't recognize them as intelligent life. They went extinct. Perhaps intelligence carries inherent self-destruction risks: nuclear war, environmental collapse, runaway AI, and most civilizations destroy themselves before achieving stable interstellar presence. We haven't looked hard enough. Maybe evidence is all around us, but we haven't been looking in the right ways or right places. The search for interstellar technosignatures, including potentially artificial objects like some claim Atlas might be, represents one approach to answering this ancient question. The Great Filter. The concept of the Great Filter suggests there's at least one extremely difficult step in the evolution from simple chemistry to galaxy-spanning civilization. This filter could be behind us. Perhaps abiogenesis, the origin of life, is incredibly rare, or the evolution of complex cells, or the development of intelligence. If so, we're lucky survivors who made it through. Ahead of us, perhaps the difficult step is yet to come. Maybe most civilizations destroy themselves shortly after achieving advanced technology. Or maybe interstellar travel is physically impossible, despite our theories. Where the filter lies has profound implications. If it's behind us, we might be alone or nearly alone in the galaxy, but our future is potentially bright. We could become the first civilization to spread among the stars. If it's ahead of us, other civilizations might have failed to overcome whatever challenge awaits us. Our survival as a species is uncertain. Finding evidence of interstellar probes, even ancient, inactive ones, would tell us the Great Filter is behind us. It would prove that at least one other civilization achieved interstellar technology and survived long enough to deploy it. The zoo hypothesis. Another explanation for the Fermi paradox. Maybe they know we're here and they're deliberately not contacting us. This zoo hypothesis suggests advanced civilizations might have policies of non-interference with developing species, similar to Star Trek's Prime Directive. They observe but don't interact until we reach some threshold of technological or social development. If true, interstellar probes passing through our solar system might be surveillance devices, monitoring our progress and waiting for the moment when we're ready for contact. This sounds like science fiction, but it's not logically impossible. If advanced civilizations are widespread and long-lived, they might have established galactic norms and protocols for dealing with emerging species. We might be living in a cosmic nature preserve, watched but untouched. The implications are both reassuring, someone's looking out for us, and unsettling, our development is being monitored and possibly guided. What if we do find artificial objects? Let's seriously consider, what would happen if an interstellar object, whether Atlas or a future visitor, turned out to be definitively artificial? Short-term effects, scientific revolution, confirmation of extraterrestrial technology would be the most significant scientific discovery in human history. Every assumption about our cosmic uniqueness would be overturned. Religious and philosophical impact. World religions would need to reconcile their teachings with the reality of other intelligent beings. Some faiths might adapt easily. Others could face existential crises. Social disruption. Conspiracy theories would flourish. Some people would panic. Others would celebrate. Social cohesion might suffer as different groups interpret the discovery through their own cultural lenses. Economic uncertainty. Stock markets might crash or soar depending on whether the discovery is perceived as threatening or promising. Investments in space technology would likely boom. Political tensions. Nations might compete to control or study the object. International cooperation could either strengthen, united by common purpose, or fracture, divided by competing interests. Long-term effects. New scientific disciplines. Xenoarchaeology, the study of alien artifacts. Comparative technology studies, exolinguistics, studying alien communication systems. Technological insights. Even an inactive probe could teach us about materials science, propulsion systems, computing architectures, and energy sources far beyond our current capabilities. Existential questions. We'd need to grapple with questions like, who built it? What happened to them? Why did they send it? Are they still out there? Should we try to contact them? Human unity, maybe. Confronting evidence of other intelligences might help humanity see itself as one species rather than divided nations, potentially accelerating global cooperation. Or human division. Alternatively, it might exacerbate existing tensions as different powers compete to control the object or claim credit for the discovery. The outcome would depend heavily on how the information was communicated to the public and whether institutions could maintain stability during such a profound revelation. The responsibility of knowledge. Those of us watching the Atlas story unfold, including you right now, have a responsibility to think clearly about these possibilities. Not to panic, not to dismiss, but to engage thoughtfully with questions that might shape humanity's future. Whether Atlas is natural or not, it reminds us that we live in a vast universe full of mysteries. Some mysteries will be solved by mundane explanations. Others might surprise us in ways we can't yet imagine. Our job isn't to prejudge the answers. It's to observe carefully, think critically, Stay open to evidence. Prepare for multiple possibilities. Communicate responsibly. Science is humanity's best tool for understanding reality. But science works best when scientists remain humble about what they don't know, curious about unexpected observations, and willing to follow evidence even when it leads somewhere uncomfortable. So here we are, with just weeks remaining until October 29th, the date that will either vindicate or refute some of Dr. Loeb's most dramatic predictions. What we know for certain: Atlas is real, interstellar, and currently approaching perihelion. It has unusual properties that warrant continued scientific attention. On October 29th, it will be hidden from Earth's view during the critical perihelion pass. By December, we'll have comprehensive new data. What we don't know: whether Atlas will emerge from perihelion on the same trajectory or a different one, whether any of its anomalous features indicate artificial origin or simply unusual natural composition, what the next interstellar visitor will look like, and whether it will be even more puzzling. What we should do: watch the observations as they come in, evaluate evidence objectively, avoid both premature dismissal and premature acceptance of extraordinary claims. Appreciate that we're living through a remarkable era of astronomical discovery. Avi Loeb may be wrong about Atlas. The overwhelming probability is that it's a natural, if unusual, interstellar comet. But he's performed a valuable service by asking uncomfortable questions and pushing the scientific community to engage with possibilities that challenge conventional thinking. Science advances through this kind of creative tension between bold hypotheses and skeptical criticism, between open-minded curiosity and rigorous evidence standards, between what we expect to find and what we actually observe. October 29th is coming. Atlas will reach perihelion, hidden from our view, and then re-emerge. We'll recalculate its orbit, analyze new data, and draw new conclusions. Maybe we'll confirm it's just an interstellar comet, unusual in some respects, but ultimately natural. That would still be scientifically valuable, teaching us about planetary formation in other star systems and the diversity of cosmic chemistry. Or maybe, just maybe, we'll see something that defies conventional explanation, something that makes us reconsider our assumptions about what's possible, what's out there, and what might be visiting us. Either way, we're about to learn something new about our universe. And that's what makes this story so compelling. Not the speculation about aliens or the controversy between scientists, but the fundamental act of discovery, of looking up at the sky, seeing something unexpected and asking, "What is that?" This is science at its best. Humans using tools and intellect to understand phenomena beyond our everyday experience, pushing the boundaries of knowledge and occasionally being surprised by what we find. The universe is vast, ancient, and full of wonders. Some are natural, some might be artificial. We won't know which until we look carefully, gather good data, and follow the evidence wherever it leads. Atlas is one small piece of this grand cosmic puzzle, but every piece matters. Every observation teaches us something. Every mystery invites us to look closer and think harder. So keep watching the sky. Keep asking questions. Keep your mind open to evidence while maintaining healthy skepticism about extraordinary claims. Because somewhere out there, Between the stars, objects are wandering, some carrying the chemical signatures of alien suns, some possibly carrying something more. And humanity is finally developing the technology to notice them, study them, and perhaps one day understand them. The countdown to October 29th continues. The universe is waiting to show us what happens next. If you found this deep dive valuable, hit that like button and subscribe for more exploration of the mysteries at the intersection of science and speculation. Drop a comment telling me, what do you think will happen on October 29th? Will Atlas emerge on the same trajectory, or will we witness something extraordinary? And what would you do if you were in charge of investigating an interstellar visitor? Share this video with anyone fascinated by space, astronomy, and the possibility that we might not be alone in the universe. Because these questions aren't just for scientists, they're for everyone who looks up at the night sky and wonders what's out there. Until next time, stay curious, stay skeptical, and keep watching the skies. The universe has more surprises in store, and we'll be here to explore them together. This is your host, reminding you that science isn't about having all the answers. It's about asking better questions. And right now, Atlas is asking some of the most provocative questions in modern astronomy. We'll see you in the next video. Clear skies and keep questioning everything.